Everyone, well, we will be continuing our fun-filled day here on PALS TV. We're going to be heading over to another part of Columbus now, to our PALS program there. For our next segment, joining Professor Phil for a very cool science class and lesson. This is I guess our version of Mr. Wizard's World. So we have some excellent classes for you already this week that we've put together from our Columbus location, and I know this will be no different. It should be a lot of fun. I can't wait. I always loved, with science and mixing different things together and seeing the reaction. So really looking forward to it. Professor Phil, the class is yours.
Today, we're going to learn how to make plutonium from common household materials. Not really, that would be ridiculous. We're going to do some basic household type of chemistry. All of this stuff is stuff that you can do at home with things you can easily get yourself. But the first thing we need to do is to make sure that we're keeping ourselves safe, because even the stuff in your house can be dangerous. So the first thing we need is to put on our lab coat. Now, some people are going to need the lab coat just so you don't get your hands dirty. And that's important, but it's not nearly as important as some kind of acid spills on you. You can rip that lab coat off really quickly so it doesn't get on your skin. That's the real purpose of a lab coat. Not just to keep you clean, it's to keep you safe. And if it gets on your skin, it's bad. If it gets in your eyes, it's worse. So always wear your safety goggles. Safety goggles at all times. In most of the things we're going to be doing today, I will also be wearing gloves, but not for this first bit because all I've got here is water. It is water with food coloring, and I don't want it in my eye, so I'm still wearing my goggles. Protection, protection, protection. We're going to be moving around the room a lot, so if you've got issues with vertigo, I'm going to be moving this camera with no sense of what I'm doing, so look away when I switch. This first one, we're going to start, we're going to do something else for a bit, and then we're going to come back to see how it works. Right here, I have 3 empty cups, and then 4 cups with colored water. It's just water and food coloring, nothing fancy here. There's red on either end, a yellow, and a blue. And I've got a long piece of just basic folded paper towel. Stick this in the end, put a corner in there, get it in that yellow, try not to knock everything over. Get it in the blue, not knock that over, and get it in the red. You can see that this is starting to come up on the paper towel already. It'll take a while to get where we want it, but this is what we call a capillary action. Paper and paper towels, cloth, things like that, they're just woven together, so we have a lot of tiny little holes and tiny little threads. Water, you might not think of it, but it's fairly thick. Water likes to stay together. That's why little drops get near each other and they make big drops. So as the water wants to stay together, a little piece of water goes up into those holes in the cloth, and then it wants the rest of the water with it. So the rest of the water follows it, and it keeps going up. If you can see here, let me get a little closer, I'm moving. The red has already come up near to the top of that. All right, so we're going to leave that to go for a little while, and we will come over here. This is going to swing a lot. Don't knock over your graduated cylinders. It's a bad idea. All right, so Show of hands, have we ever done the make a volcano with baking soda and vinegar? Oh, I thought there'd be more hands than that. Okay, it's a classic. What happens there is that you have the baking soda right here, which is a base, and it's specifically sodium bicarbonate. A base is something with a high pH, and all that means is that it's a base. Bases are the opposite of acids. Both of them can hurt you very badly, so you want to be careful. Bleach is a base, and it can burn your skin, so you want to be careful with both acids and bases. When you add an acid and a base, you get a strong reaction. When we add the vinegar to the baking soda, it starts breaking everything apart, and we get a bunch of foam. All that foam is carbon dioxide, the same thing you breathe out every day. But you don't need to use vinegar. You can use other things, as long as it's an acid interacting with a base. You got to be really careful with this because that can be very, very dangerous. Adding anything to bleach will probably create a poisonous gas that will kill us all. Never add anything to bleach. Scoot this back just a touch. As you know, the lemon is a citrus fruit. It's a citrus fruit because it has citric acid in it. That is a type of acid, and this will work just as well as vinegar. If anyone was here yesterday, you know that if you want a lot of juice out of a lemon, you got to heat that up and give it a roll. Just a roll will do. You got to break it apart. I've already heated this up and rolled it and started to open it up. But we're going to take the top off this lemon with my handy multi-tool. We'll just rip into it. Remove the top, set it aside. Which side that should go on. And we've just got an open lemon, and I just poured lemon juice all over my hand, so that was great. This is why I was supposed to put on the gloves already, which I'm gonna do now. Remember, safety first. Oh, gloves on. So lemon juice isn't going to hurt me. However, I'm going to touch a bunch of other stuff throughout this. And if I get lemon juice on that, it might create something that will hurt me. I should have picked bigger gloves. Normally, you don't blow in gloves to open them, but I'm not actually working with anything that's going to kill me right now. That's good enough. I'm just holding this lemon. I'm going to take this normal bamboo skewer, poke some holes in this here lemon. We want plenty of juice to come out. And because colors make it more fun, red food coloring. Oh, that does not. Dip a little food coloring in there. You don't need much. Give a little squeeze. Ooh. All right, now it looks like I've just slaughtered this lemon and it's bleeding all over the place. More exciting. Don't want to get water in there. We'll take a little bit of the baking soda and just dump it right in our lemon. By a little bit, I mean way too much. I keep this stuff by the 5-gallon thing. I should let you know that I have tested none of these before you've seen them. They might work. They might not. I don't have any idea. That's why it's science. We learn together. Oh, there we go. This is not the most energetic reaction, but you can see this foam coming up. We have a little squeeze, get a little more juice in there. Again, all this is carbon dioxide. You can get a bunch of these put them out and do them in different colors. The best part about this one is that it also smells really nice because it's got this lovely lemon scent. See if I can get any more in there. I think this is probably going to continue to go. So we'll come back and look at it later, see how much we can get. I'll put it in a bowl. We're going to put that in a beaker, see how it goes. The important thing also, always, is to keep things clean. As much as you can. Most of this is not going to be very clean. All right, we're going to switch over here now. Again, if you got vertigo, look away now. Bring that one down some more so we can see this plate. Now I'm going to wipe off my hand. Let's move up for just a second. I've graduated cylinder here. All this has is some warm water in it. We're not going to use this right away, but we need to start this process for our big finale. Here I have basic dry yeast, the same stuff you buy in the grocery store when you're making bread. We remove the cork, and we dump the yeast into the warm water. Dump. Put that one back up. That did not go back up very well. And we give it a little shake. Oh, that one really solid. Try and get this up. I'm gonna have to use my stirring stick. I have a tiny bit of sugar in this water. Yeast is a living animal, and it likes to eat sugar. So when you take dry yeast, or wet yeast as well, and you put it in a little sugar water, the yeast start to eat that sugar. And as they do that, they have to get rid of something. When you eat stuff, you have to eliminate afterward. You need to go to the bathroom. That's what happens to the yeast as well. And yeast produce carbon dioxide when they eliminate. Their bathroom is just gas. That's a very useful thing for a lot of different reactions. Again, all we had with the foaming lemon was carbon dioxide. That's part of what this yeast is going to do. But you need a little time to let the yeast start to eat and start to work. We'll set this aside for our later work. More riddleman. Again, gloves. In this case, the gloves are not just to keep me clean, but using this next demonstration can irritate your skin quite a bit. You'll want to skip that. You want to skip the irritation. You don't want to skip the experiments. Good stuff. All right, so what do we know about ice? Ice is cold, and it's just water. We are going to make hot ice, or room temperature ice, really. It is not in any way actually ice. So when we add baking soda and vinegar, like we said before, it just makes a bunch of foam, creates carbon dioxide, a bunch of little bubbles, and then it spills out all over the place like we got in our lemon. Same thing. That's not the only thing they do. If you boil and get rid of some of the water in the vinegar, and I have it here that I've colored green just because it's interesting, you get a liquid, but you also get a little powder on the edges. that powder and the liquid are sodium acetate. It's acetic acid is vinegar, that's the acetate, and sodium bicarbonate, like we talked about before, is the baking soda. So when they come together and get heated up, they break apart and they come back in a new way, and that's sodium acetate. I've got just a few grains of it here, and I'm going to pour it in the middle of this plate. And then I'm going to make, I don't know. I don't want one pile because it looks weird when you do that. Get that stuff out of here. So ice, regular ice, water ice, when we freeze water, it creates crystals. They all come together and they build up on each other. That's what we're going to do here. The reason I have the powdered sodium acetate there is to start our crystal formation. In water or other liquids, we would call this a condensation nucleus. This is what gives champagne its bubbles, and to a lesser degree, also soda. It's not just carbon. If you fill water with carbon dioxide, it won't bubble on its own. We used to think it was imperfections in the glass. There's little cracks and bumps in glass or in metal cans. So all those little bubbles of carbon dioxide form there. But we found out that isn't true. What makes the bubbles in champagne and soda is dirt. The dirt is called condensation nuclei, just little bits that all the bubbles can form around. And in this case, that all the crystals can form on. So let's look down at our plate. Again, here are our starter crystals, and we've just got a liquid. We slowly pour the liquid onto the crystals, and the liquid and the crystals are made of exactly the same thing. Oh, wow, this isn't working at all. Oh, it's working a little bit. Let's just dump it. How about that? This is why science is interesting, because this did not work at all. What should have happened was that this should have immediately formed crystal. Oh, it's slowly happening. Let me show you what this is doing. What should have happened is that it immediately crystallizes and we would get a tower building up. That did not happen, but we get a bit. As I pour it back in, I don't know if you can see how thick that is at this point. Well, it's become a lot thicker than just a liquid. It didn't go the way we wanted. So the question is, why? And that's the interesting part. What makes this different than it was supposed to be? My guess is that it's not cold enough. To do this, and why I had to start early today, you need to first heat up and boil your vinegar and your baking soda. And when they boil down, get rid of all the water in the vinegar, then you cool it down. I'm going to guess I didn't spend enough time cooling it down so that when it hit, it didn't work. The other possibility is that the pan that I used wasn't perfectly clean and something got in there that affected how this would work. Always clean your labware. And clean everything else too. You do something, you clean it up. It's just a good practice. Because this stuff can irritate my skin, I'm going to take these gloves off and put them on the sign because I don't need to hurt myself with that. All right, let's go back over here and look at our colors again. Well, you can't see that yellow very well in this light. For everything else, you can see the red has moved well up. I need to get touched down a bit. This blue, particularly, has gone everywhere. And this red right here is meeting. The yellow's gone quite far too. You just can't see it yet. Again, this is capillary action. Water likes to stick together, so water just slowly goes up the cloth. All right. I'm going to want to move the computer back a little on this one because if this one works, and I really hope it does, it is going to be an excessive mess. In my Erlenmeyer flask here, I've got hydrogen peroxide, the same stuff you might use on cuts. This is a stronger version. It's the kind you use if you're dyeing your hair. And I put blue food coloring in it because I think it would look better if it's blue instead of clear or whitish. All right. Hydrogen peroxide is not harmful in itself, but I'm going to do some things to it. We'll make it not terribly pleasant. So gloves on, because we're always safety first. Maybe we should spring for the powdered gloves next time, get these on easier. All right. So we have our yeast from before, and we've got hydrogen peroxide. As you might guess from everything we've talked about before, hydrogen peroxide is just a hydrogen atom and some oxygen atoms, more than one hydrogen atom. What's going to happen when these get together is that all of the oxygen in the hydrogen peroxide is going to get released. So just like the carbon dioxide that came out of our baking soda and citric acid in our lemon, we're going to create a bunch of gas bubbles if all this works. I think that our yeast should be ready by now. It seems a little cool. So we're going to take our yeast and we're going to pour it into our Erlenmeyer of hydrogen peroxide. I should mention this. This is called an Erlenmeyer flask. It's just a name, it doesn't matter. We pour that in. And the yeast is all stuck in there. Fortunately, we've got our stick. Pull your yeast down. Remember to keep your face away from the opening of any glassware you have. You do not want to breathe in anything that's putting out. In this case, it's just oxygen. It wouldn't be that big a deal. But always go with your general rules. Mixing that up. Check that out. Keep that reasonably clean. We'll give this a swirl. That is not as epic as I thought it was going to be. Let's see if we can get more. A good swirl. All right. I'm going to dump this into this one so we can see. So what was just a fairly thick liquid is now this. I wish this was more energetic and spilling all over the place, but it is a reasonably good amount of foam. Oh, I can stir it some more, get some more in here. Oh, I can see more blue coming out. This is going to keep going for a ridiculously long amount of time. If you were here and were able to touch this, and again, everything in here is perfectly safe. Ooh, yeah, that's quite warm. It's not hot, but it is warm. So when we break apart the hydrogen and the oxygen, we're creating heat as well. This is what we call an exothermic reaction. Exo means out, and thermic means heat. So it's sending heat out into the world. The opposite of this one would be an endothermic reaction, where all the heat goes inward. Generally, you get a good explosion if that happens. And if it's fast enough exothermic, you get an explosion then. In this one, we're just getting bubbles that are continuing to go. Turn that up more. Oh, it's getting really warm now. All right, you've been right on top of this and looking at the top as it's coming out. So you're missing a fair bit of what I got here. Put the gloves off. This is the kind of foam we're creating. There's a fairly good amount of it. The stronger peroxide you use, the more foam you get. So at least 20 volume if you're using the hair stuff. You can also do this with the regular peroxide that you've got in your medicine cabinet probably right now. It won't be nearly as much. This is quite a bit of foam. All right, let's go back and look at our capillary action again. They do not seem to be connecting at all. All right, so we've got these through. I'm not certain. It's quite light, but we can see where the blue and the red are coming together. There's some purple that's starting right in the middle there. There's not a ton of it yet. Let me see if there's any green on this one. Oh, not quite yet. Not any orange at the moment. But that's where we're going. We can start to see how these colors will come together. Where it's just been white and there's nothing in these, there are new colors that are coming out. This is just your basic color science here. Put red and yellow together, you get red and yellow. Red and yellow together and you get orange. Blue and yellow make green. Red and blue make purple. That's right. Way to go. All right, there's foam all over the place now. That's why you got a lab coat. Let's continue to look at the extending foam. All right, so there's a lot of different things you can do at home. Basic chemistry, and we can figure out how things react. When you do this, you need to make sure that you're doing it as safely as possible. Wear your goggles or whatever safety glasses you have. Wear something to keep you not only clean, but something you can take off quickly if something dangerous spills on you. Wear gloves if you need them. If you're just using water, that's not a big deal. You'll be fine. But if you're doing something like this, you're going to want gloves. I don't really want to touch this with my hands right now. Again, the lemon that we did, gloves aren't really necessary, except it's quite a bit of a mess. So we're going to want gloves for that. But lemon juice isn't going to hurt you unless you got a tiny little cut on your finger, and then it'll hurt a lot. Next time, we're not going to do the same experiments unless I can get the hot ice one to work. I'm going to try that over this next week and see what happens. We will be doing different things, probably some physics then, and we'll definitely be playing with fire. So that'll be an exciting time, but again, could be dangerous, so let's be safe. Any questions or anything you want to see in science that you'd like to learn about? Opening it up. Yes, Caitlin?
Make crystals.
You want to make crystals. Most of the ways that I know to make crystals take some time. So if we're going to do that, we're going to have to make sure we show up from week to week. In fact, if we're doing that, we might as well make plastic from milk. So we can start that next week, but it takes a few days for that to get solid. So we can start that as well. It's an excellent idea. Anyone else want to see anything really interesting?
Do it. I want to see bacteria. No, I'm good.
To see bacteria.
I want to see bacteria.
I'm not sure that I can find a way to do microscopes on here, but I'll try and figure it out and see what we've got. One thing I know we can do is that we can see DNA. I can make DNA big enough that we can see it. So we'll definitely try that at least, and we'll see what we can do about bacteria. Caitlin?
Again, the COVID.
Hang on, Caitlin. Start over again. You weren't unmuted quite yet.
The COVID thing. Remember when you did the Monday? Was it Monday?
Oh, that?
Yeah, did I again?
Oh, yeah. Okay. That's pretty much what we did with the lemon. It's about the same thing. Anybody else have any wild ideas they want to see? All right, well, we're a little early, but these kind of ran through pretty quick, so we'll kick it back over to continuity. We'll see you next time.
What about Petri dishes, Phil?
Petri dishes may be the best way to actually see bacteria that I can think of, yeah.
Yeah, that's what came to mind. I mean, I don't know how we can get microscopes tied into here.
Yeah, it'd be tough.
We could ask around, though. I
Yeah.
like this. That's a great one. Though.
Candy walk.
What's that, Caitlin?
The candy walks, like you put make a candy walk,
You just want something to eat, don't you?
like candy walk, walk candy.
Yeah.
They crackle in your mouth when you eat them, right? Yeah, I remember those. How did they make rock candy, Phil?
That's just a simple sugar crystallization thing. The same thing we tried to do with the hot ice that didn't work out. You just get condensation on a piece of a stick or string that's sitting in sugar water, and as it crystallizes, it keeps forming on top of itself until you get a great big chunk of sugar.
Very interesting.
Go ahead, you're unmuted.
With a pop rock.
I'm pretty sure we can make pop rocks too. I don't know how yet, but we can figure it out. So we can do all kinds of science with food and stuff we can actually eat after we play around in the lab.
What about the things that you made earlier, Phil? Has anything changed with the lemon or the ice?
I might as well try the ice again. The lemon has kind of lost all its fizz, so just kind of looks like a blood orange now. Go ahead. I'm gonna stir this up. There's a lot of stuff in here. You can see this weird film there. That's where it started to crystallize on the inside. Normally, you have to be really careful because if you shake this at all, it goes. We got the chunks, but it is not creating a really cool tower. Disappointing, but not that disappointing because we still learned something. That this doesn't work the way we did it. Now we just have to do it a couple different ways to figure out what didn't work and what we actually messed up.
So with science, you always have that hypothesis in the beginning, right? So you come to that educated conclusion. What do you think?
You come up with an idea and I say, this is probably what will happen with what I know about how the world works. And then we test it. Sometimes the test is a negative, which is never a failure in science. That just told us that our idea was wrong. Now we got to create a new idea to explain how the world works.
And that's so valuable right now because that's one of the most important aspects of getting us through what we're currently living with, you know, and the scientists and some of the experiments that are happening in these labs. I'm trying to find the vaccines. And that's really what they're doing, is what Phil showed you today, trying out different chemicals and seeing the reactions and then testing them to see how it works. Wonderful. Well, thank you, Phil, for that science lesson. Did a wonderful job as usual. I think we're going to break here for about 20 minutes, so a little bit longer, but it's a perfect break and a nice end to our day. As you can see, I changed, go get in some comfortable clothes because we're going to be exercising to finish in our day and doing some self-defense and empowerment courses. So that should be a lot of fun. Really looking forward to that. So we'll be coming back live from Gallia at 3 p.m. But again, thanks, Phil, Professor Phil from Columbus, and your science course today. We appreciate it.
We'll see you guys tomorrow or next week.
All right.